Hi, today I am going to explain about Module 2. In this Module 2, the first topic, which is Principle of Operation of BJT. When we see this Module 2, which consists of the operation of the PN junction diode and characteristics of PN junction diode. In this characteristics of PN junction diode, we have a common base, common emitter, common collector configurations, and a load line analysis for those configurations. And second part, which is the most important part, analysis of hybrid parameter model for transistor and conversion of H parameter models. The first part, which gives the details of the transistor, and the second part, applications of the transistor. Let us see that now the basic principle and operation of the bipolar junction transistor. Bipolar junction transistor are simply BJT, which was developed by Dr. Shockley along with the Bell Laboratory. The BJT is a main building block of all modern electronic systems nowadays. Of course, that BJT replaced with the UJT, a FET or MOSFET, or sometimes today technologies. But anyway, the transistors plays a major role in the modern electronic systems. And it is a current control device, whereas BJT is a voltage control current source. It is current control device means the BJT which controlled by the current. When we see this current control in the operation, and also it is used as the primary component in the amplifier. When we see any amplifier without a transistor, no one amplifier was there. So the main heart of the element of amplifier is that transistor. So that's why we are going to discuss about the operation of the BJT and its applications in this module 2. A bipolar junction transistor has a very important property that it can raise the strength of the weak signal. This property is also called amplification. By the property of this amplification, this BJT is widely used in electronic devices and all semiconductor devices. And at present, the transistors are widely used in digital computers, satellites, and mobile phones, and other communication systems and control systems and all electronic systems. And this BJT basically is a bipolar. Why it is called bipolar means the current flow in the BJT is due to both the majority and minority carriers, both electrons and holes, due to which it is called bipolar. Whereas in some other transistor, in contrast FET, field effect transistor, it is a unipolar in which the current flow in the FET is due to only majority charge carriers. Coming to the construction of BJT. This construction is very important and very interestingly how they design of 3-layer device. When compared with the simple PN junction diode, it is quite different in a construction and operation. Just adding 1/3 layer is quietly important possess the important characteristics in BJT. Let us see that construction of this BJT. It is a 3-layer of which are called emitter, base, and collector. And base is very thin. Emitter is in moderate, and the collector is in large size. Which represents the size of these 3 layers, size of these 3 regions. There is a particular reasons why base is thin region and the emitter is moderate in size and the collector is large in size. If you see that emitter, why it is moderate in size, actually these 3 layers start from left side. First one is emitter, second one is base, third one is collector. When we see this emitter, base and collector, the size of this emitter is moderate in size, base is very thin and collector is very large in size. Because of this size with the different proportions, the transistor having different characteristics. Emitter is moderate in size because which emits more number of charge carriers, and base is very thin because which transport from emitter to collector by passing through this thin area. When the area is very large, it fails to amplification. And the collector is very large in size, so that when large number is coming from emitter to through base, so collector is withstand to collect all the charge carriers coming from emitter. Similarly, when we see the doping, first layer emitter is heavily doped, second layer base is lightly doped, third layer collector is moderately doped. When we see the doping, why it is called emitter is heavily doped? Because emitter is the first layer which emits more number of charge carriers. So emitter is heavily doped due to which emits large number of charge carriers which are going through the base and reach to collector. So in order to get large number of charge carriers travel from emitter to collector, so emitter is heavily doped. Due to heavily doped, more number of charge carriers are generated in this region. And base is lightly doped. When the base is lightly doped, so whatever the charge carriers coming from heavily doped emitter and passing through the base, recombination takes place. When it is heavily doped or moderately doped, so moderately it is recombination takes place, or if it is heavily doped, large number of charge carriers or recombination takes place in the base region only and cannot reach to collector region. So that's why if base is very lightly doped, then less number of recombination takes place in the base region and remaining almost all charge carriers are reached to collector. And the collector is moderately doped. So whatever the charge carriers just bypass just pass by this base region and reach to collector. So whatever the charge carriers are reached to collector, in order to recombine all those charge carriers coming from emitter through base can be combined in the collector region, so that collector is moderately doped. So these two important things, one is doping and other one is the size of each layer. The doping of each layer is different and size of each layer different. Combining these two properties of these three layers can become transistor act as an amplifier, and can become this three-layer device which makes useful in amplification. Basically, there are two types of bipolar junction transistors. One is NPN transistor, another one is PNP transistor. In the NPN transistor, emitter and collectors are made of N-type semiconductor materials and base is P-type. And the PNP transistor, emitter and collectors are P-type and base is N-type. Two N-type materials are sandwiched with the P-type material which is called NPN transistor, and two P-type materials are sandwiched with the one N-type material which is called PNP transistor. These two types of transistors are used in this electronic devices. This is the simple representation of how NPN and PNP transistors formed. Take the two PN type materials and sandwich with a lightly doped and very thin region of base type. When we connect it, we'll get NPN transistor. Whether it is NPN transistor or PNP transistor, the first layer always must be emitter, and center layer always must be base, and last layer always will be treated as collector. Similarly, in the PNP transistor, two p-type materials are combined or joined with the base N region, and this is the symbol for NPN transistor. Take the three terminal in a 45 degrees, and one center terminal is taken as base, and this terminal is taken as emitter, and this terminal is taken as collector. The arrow indicates the direction of current flow, and the end point of this arrow which represents N type. For example, if it is a NPN transistor, you start this arrow point as N, remaining automatically N, P and N. Whereas in P-type material, PNP transistor, the symbol is like three terminal, one is base, and this one is emitter, and this one is collector, and the direction of arrow towards to the device. So this direction towards the device which represents the PNP transistor, and the end of the arrow represents the N type. So when N is center, remaining is P-type, PNP transistor. Most of the times in the circuit analysis, instead of using these box types of representation of PNP and NPN transistor, we can simply use this kind of symbols in the network analysis. If you see simple analogy of this bipolar junction transistor from PN junction diode. So as we know that this is a 3-terminal PNP transistor and 3-terminal NPN transistor, and left one is emitter, center one is base, and last one is collector. And if you take this is 2 diode analogy, first 2 layers which is represented with the PN diode, take the PN junction diode, and second time when we devise this base region divided into 2 parts. So this P-type and first half of the part of base region is called PN diode, and again here also this N-type and P-type is nothing but another PN diode. So the back-to-back connecting of this PN junction diode is nothing but PNP transistor. Similarly, this N-type and one half of the P-type made base is treated as N-type and P-type, and again this half part of the P-type and N-type will be treated as PN diode. So this back-to-back connection of this p-type material connected together to get a NPN. But really it's not happen. Take the two PN junction diode and back-to-back connected to get the PN junction diode transistor. Just it's only to analyze analysis purpose. Like it is analogy to understand these three layers getting from two PN junction diode. Okay, when we see these symbols, the transistor symbol, whenever the arrow direction of arrow towards to the device or the arrow away from the device, this arrow towards to the base terminal, then it is called PNP transistor. Whenever it is away from the device, it is called NPN transistor. So here in this case, this this terminal is called emitter terminal, this terminal is called collector terminal, this terminal is called base terminal. The current flow in the emitter terminal is called emitter current IE, current flow in the collector terminal is called collector IC, and the current flow in the base terminal is called IB. And voltage between emitter terminal and base terminal is called VBE or VEB, and voltage between collector with respect to base is called VCB, and voltage between emitter terminal and collector terminal is called VCE. So these current parameters IE, IB, IC and three voltages are helpful while analyzing or understanding the characteristics of BJT. Similarly for NPN transistor also, this emitter and a collector current and a base current and three voltages between three terminals. So BJT has two junctions. One is emitter base junction and the second one is collector base junction. So finally we can simply say that BJT is a three-terminal two-junction electronic device. Let us see how these two junctions are formed and the importance of the two junctions. This device is called bipolar junction transistor because current is due to motion of two types of charge carriers which are called free electrons and holes. Let us see. So far we know that the construction and the size and doping of each layer. Why each layer having different in size and different doping. Now let us see that the open terminal bipolar junction transistor. As I said, this emitter for example, this is the emitter region, this is the base region, and this is the collector region. When we see the size, moderate, very thin, large in size. When we see the doping, it is heavily doped and lightly doped, moderate in doping. Okay. So in a PN junction diode operation, as I explained in the previous lecture, P-type and N-type initially electrically neutral, but when we connecting together P-type and N-type material, even if you see here P-type material is a heavily doped P-type material, emitter layer is heavily doped. So the representation of this P-type material with the minus with circle and a hole, excess hole, minus with circle, minus with circle, minus with circle. So this kind of representation for p-type material is that all acceptor atoms added to trivalent atoms added to intrinsic semiconductor to get the p-type. This minus with circle represents this added trivalent atom with a vacant space called hole. This representation of p-type having excess holes, whenever this semiconductor material excited, these excess holes or free holes are first excited. So the representation of this p-type is a minus with circle. So when we receive or accept one electron, and then it fill the covalent bond, and it will become as a negative ion. Similarly, in the base region, so base is a n-type material. N-type material represented with a plus with circle with a free charge carriers, excess electron or free charge carriers. So this kind of representation, free charge carriers in the n-type plus with circle, where plus with circle represents the donor atom or donor ion, and the dots represents the free charge carriers in the n-type material. But when we see the doping, emitter is heavily doped and base is lightly doped. So when both are electrically neutral and when we connecting together, due to concentration gradient, this majority charge carriers of holes on p side is more than minority carriers of holes in n side. So the concentration gradient, for example, here it is 12 holes on p side and only 2 holes on n side, minority carriers in the n side. So due to this concentration gradient, one region having more number of charge carriers like holes in p-type and less number of charge carriers on n side. So this concentration gradient, they have a tendency to move from higher concentration gradient to higher concentration to lower concentration. So same thing happened as p-junction diode. So this concentration gradient makes these charge carriers like a free charge carrier from n side and free holes from p side move together, cross together. When we cross together and recombines together, and it will become as a ion, negative ion, that can be represented in this region. This much of negative ions accept all electrons coming from the base and fill the covalent bond, and it will become as a negative ion. So this can be represented with this minus on p side, like emitter side. Similarly, whatever the base region having electrons, donate these electrons, excess electrons are free charge carriers of electrons, and it will become as a positive ion, and then the plus with circle, it will become as a positive immobile ion on n side or in base side. And one more important observation in this here, the less number of minus with circles formed on p side and more number of plus with circle formed on n side, due to which the different immobile ions formed on p side and n side. The reason is p is heavily doped and n is lightly doped. When more slope on n side, more slope on n side, so more number of charge carriers tendency to move from 12 to 2 side. When more number of charge carriers have tendency to move from this higher concentration to this one, heavily doped p-type to lightly doped n-type, then the more number of recombined holes are with the electrons. So that's why in the n side more positive immobiles are formed than the p side, negative immobile ions. Similarly, here, so this negative immobile ion on p side, one line and three lines of positive immobile ions are called depletion region. And this depletion region formed between emitter and base terminal. That's why this depletion region or this junction is called emitter base junction. The junction formed between emitter and base terminal is called emitter base junction. And the junction formed between collector and base region is called collector base junction or collector junction. Here also, initially, this base region of n-type material and collector region of p-type materials are electrically neutral, and once joined together, connected together due to concentration gradient, so less number of charge carriers in base side than the more number of charge carriers on p side. Due to this concentration gradient, the majority charge carriers of holes from p side and majority charge carriers of electrons in the n side are crossed together, recombined together, and then form this negative immobile ions on p side and a positive immobile ion n side. So that here the junction will be formed between base and collector. So that a p-n junction diode, so that in the bipolar junction transistor, two p-n junction diode, two depletion regions are formed, and these two depletion regions are different regions in emitter base junction and different size in collector base junction. This circle, this dots represents the free electrons, and this minus with circle represents negative ion, plus with circle represents positive ion, and this white symbol represents the holes. Now, this is open terminal p-n junction BJT, bipolar junction transistor. I'm without providing any biasing to this three-terminal bipolar junction transistor due to concentration gradient. This junction between p-type and p-type emitter and n-type base, and another junction formed between base and collector. Now we will see that once they formed two junctions between emitter base and collector base junction, now we will see that operation of bipolar junction transistor. The operation of the bipolar junction transistor can be explained with the two cases. One is keep the emitter base junction is forward bias and the output collector base junction is 0. And second case, keep the input emitter base junction is 0 and then collector base junction is reverse bias, and let us see the behavior of the device. And when we combine together, then we'll see that what is the complete operation of the bipolar junction transistor. Let us see that first. The emitter base junction, this is the emitter layer and the base layer. Emitter base junction is forward bias. So by connecting the positive terminal of the battery to the emitter layer and the negative terminal of the battery is base layer, and then it is said to be forward bias between emitter and base, and keeping this collector base junction is 0. In order to understanding the emitter base layers operation, by keeping the output junction gets 0. So when we connecting in this way, it is just like a p-n junction diode connection. a PN junction diode in forward bias. When the PN junction diode is in forward bias, as we know that the majority charge carriers of holes in p-type are repelled by the positive terminal of the battery, and majority charge carriers of electrons in n-side repelled by the negative terminal of the battery. Then the direction of the majority charge carriers from emitter to junction and majority charge carriers of holes from base to junction. When they are crossed together, the majority charge carriers are crossed towards to the junction, then the recombination takes place, and then the moving of charge carriers inside the device, then the current flow from emitter to base. So it is simply quite simple operation of PN junction diode is in forward bias. So this already emitter is heavily doped. It emits more number of charge carriers, and whatever the emits more number of charge carriers are recombined with the base region, and then the moving of charge carriers from emitter to base, then the current flow from emitter to base in this case. And then because of base is very thin, whatever the charge carriers emits from the emitter is huge number, that is recombined in the base is very less, and the remainings are entire things reach to collector region. Now we will see, by keeping input junction is 0, or by keeping input battery is 0, battery which is between emitter and base, and then see that by connecting battery between base and collector, and also by connecting reverse bias connection between base and collector. I'll tell you the reason why we take this case. This emitter base junction is forward bias and the collector base junction is reverse bias. It is a quite common connections for an amplifier. So that's why we have seen that operation of the PN junction diode for this amplifier case, like emitter base junction is forward bias and the collector base junction is reverse bias. So second case, the reverse bias junction of PNP transistor. In this reverse bias base junction of PN junction transistor, collector base junction is reverse bias. Negative terminal of the battery is connected to P-type, and positive terminal of the battery is connected to N-type. When plus is given to N-type and minus is given to P-type, it is said to be a reverse bias connection. In the reverse bias connection, what happened? This minus terminal, negative terminal of the battery, and majority charge carriers in P-type are attracted. So these are opposite polarities, negative of the battery and plus positive terminal of the holes and positive polarities of holes. So all majority charge carriers of holes which are in the P-type are attracted by the battery negative terminal, and all majority carriers are in the N side are attracted by the plus terminal of the battery, so that majority charge carriers are away from the junction towards the battery, so that depletion width is increases. So the depletion width gap is increases. So it will act as open circuit. In reverse bias PN junction diode, it will act as open circuit. Junction depletion width is more. So in this case also, as we goes on increasing the reverse voltage, so this depletion width goes, it's increased. So in this reverse biased connection of collector base junction, which makes the collector junction width is increases. Whereas in emitter base junction forward bias, due to forward bias, the junction between emitter terminal and base terminal is very thin. It is most important observation in this first case, and this collector base junction width is more due to reverse bias. When we combining these two cases, forward bias at input side and reverse bias at output side, we will see the clear picture of the operation of the p junction diode. Both biasing potential have been applied to PNP transistor with the resulting majority and minority carrier flow indicated in this figure. And it is to be noted that the width of the depletion region indicated clearly which junction is forward biased and which junction is reverse biased. As shown in the figure, the large number of majority carriers will diffuse across the forward biased junction into N-type material. Since the sandwiched N-type material is very thin and it has a low conductivity due to low recombination takes place in this very thin layer, and a very small number of these carriers will take this path of high resistance to the base terminal. So always base terminal having a less current flow, which is measured in microampere current compared with the current flow in the collector and emitter is milliampere. The large number of these majority carriers will diffuse across the reverse bias junction and move into the p-type material connected to the collector terminal. So this can be represented, and this we can see see this picture. So in this picture, I am providing the forward bias connection between emitter and base. I am providing reverse bias connection between collector and base. When we combining together and see the direction of the current flow and the effect of current flow, the essentiality of this, the arrow indicates, and the width of the junction between emitter and base and width of the junction between collector and base. So here, due to forward bias between emitter and base, the large number of charge carriers, majority charge carriers, moving from P side to N side and cross the junction. When they are crossed the junction, this huge number of charge carriers, majority charge carriers, are recombined in the base thin region. Only less number of charge carriers are recombined here. Less number of charge carriers recombined here. And the remaining, for example, 100% charge carriers coming from the emitter, and only 5% is recombined in the base region. The remaining 95% charge carriers are cross the reverse bias p-n junction and reach to collector. That's why here I am representing with the big arrow. This big arrow represents the majority charge carriers flow from emitter through base and collector. The 5% charge carriers represented with a small arrow. So when compared with the 95% charge carriers flow, this is very thin. That's why it is represented with a small arrow. So here, this is due to forward bias p-n junction between emitter and base. What about reverse bias? At the same time, when we connecting the reverse bias and increasing the reverse bias voltage, so junction width increases, majority charge carriers away from the junction and towards to the battery, but minority carriers cross the junction. So whatever the minority carriers in the N side holds, small minority carriers move towards to the junction, and minority carriers in P side electrons towards to the junction. The recombination takes place, and then current flow between base and collector. But this minority carriers effect is very low, very less, because only less number of minority carriers in the N side and P side. That moving of minority charge carriers from P side to N type base to P type collector. So the direction of the minority carriers of holes from base N side to P side. So this indicates the minority charge carriers holes. These are the majority charge carriers of hole direction and minority charge carriers hole direction from base to collector. So this big arrow representation of majority charge carriers reach to collector, and the small arrow which indicates due to the reverse biased between collector and base combining together to reach collector, so that the collector current IC is equal to, which is due to both the majority current from forward biased emitter base junction plus minority current due to reverse bias junction between base and collector. So total current can be constituted, which constitute from I majority, I minority. So when we measure the output current in each configurations of the transistor, we can consider majority current and minority current. And also the direction of these three layers and these three regions can be analyzed from Kirchhoff current law. When we take this PNP transistor direction, emitter terminal is the first terminal which emits more number of charge carriers. Here it is P-type material. So the direction of the holes from P to N side. So when the holes from P to N side, that means the direction of current is also from P to N side, which means inside the emitter terminal. When the emitter terminal, it's towards to the terminal or towards to the device, then the base current, when in this base current, the electrons are recombined with the coming of holes. So when they recombine, the electrons are moved from N side to P side. The current direction is opposite. So that's why the base direction is outward direction. When the holes are these holes, majority charge carriers of holes reach to collector and reach to collector terminal. This minority carriers of holes reach to collector terminal, so that the combination of this majority and minority carriers of holes reach to collector, then the direction of the current is away from the collector. So when we see this, the total charge carriers emits from emitter is inward direction according to the KCL Kirchhoff current law. The total entering current is equal to leaving current IB plus IC. In the PNP transistor, PNP and in NPN transistor, it is direction away from the terminal emitter. The remaining base and the collector currents are towards to the terminals. So that it will satisfy the Kirchhoff current law. So the total current IE is equal to sum of base current and collector current. So in both cases, NPN transistor and PNP transistor, the direction of the current is always follows the Kirchhoff current law. So emitter current, total current is equal to sum of base current and collector current. In this case, emitter terminal is N-type material, base terminal is P-type material, and the collector terminal is N-type material. So emitter base junction forward bias, collector base junction is reverse bias, forward bias, which is reverse bias. In this case, when we connecting forward bias between emitter and base, reverse bias between collector and base, this minus terminal is connected to the N-type material, plus terminal is connected to the P-type material. This is forward bias connection. When it is minus terminal is connected to N-type, majority charge carriers of holes majority charge carriers of holes, excess holes or free charge carriers, repelled by the minus terminal of the battery and move towards to the base region. When moved towards to the base region, similarly, at the same time, majority charge carriers of holes in N side in the base region move towards to the junction. And move towards to the junction, recombination takes place and it will donate electrons, fifth electron, and it will become as a positive ion on N side plus immobile ions on N side, emitter side, and a negative immobile ion base side. So that junction will be formed, but it is very thin compared with the collector base junction. So this here, which represents the black dot combined with the white dot, represents recombination of hole and electrons. So base region is very thin, only less number of charge carriers, electron and holes are recombined in this base region. So that current flow in the base is also very thin, very less. When come to the reverse bias connection, plus is given to the N-type collector and minus is given to the P-type base. It is said to be reverse bias. When it is reverse bias, majority charge carriers of holes like white color dots represents the holes attracted to the battery, and majority carriers of electrons represented in black color attracted to the plus terminal of the battery. Then all majority carriers are away from the junction. Then the junction width will be increases. Large junction width, widened junction width, widened depletion region between collector base junction. So this can be represented with minus with circle, minus negative immobile ion are formed on base side, and plus is formed on collector side, so that junction width will be formed. So in this case also, due to forward bias, very thin junction, very thin depletion region. Due to reverse bias, very wide and depletion region. And then direction of the current flow. So according to the forward bias connection, the majority charge carriers of electrons direction is this way. When electron direction is from N side to P type base, then automatically the current direction is opposite. When the current direction is opposite, the direction of emitter current is away from the terminal. When it is emitter current is away, then remaining base current and collector current is towards to the device. So it follows the Kirchhoff current law. Total outward current direction is equal to inward current direction IB plus IC. IA is equal to IB plus IC. So this is the working principle of Npn transistor, and in this Npn transistor, when input junction is forward biased and output junction is reverse biased, due to this forward bias, large number of majority charge carriers of electrons move from emitter terminal to the base terminal, and in this base region only less number of recombination takes place. When less number of recombination takes place, only less current flow in the base region. Remaining 95, only 5% of charge carriers are recombined. The remaining 95% of electrons, majority charge carriers of electrons, cross the junction, reverse bias junction, and reach to collector. Similarly, due to reverse bias junction in between collector and base, this reverse bias junction, minority charge carriers of electrons in the base region, less number of minority carriers of electrons from base region to reach to collector. They are only minority carriers. That's why I am representing small arrow. These two arrows, one arrow represents the minority and a big arrow represents majority charge carriers in the NPN transistor. The total collector current reach the total collector, the charge carriers reach to the collector both minority charge carriers and majority charge carriers. The total collector current due to IC is equal to total IC current due to majority charge carriers plus minority charge carriers. So that IC is equal to IC majority plus IC minority. Total current which follows Kirchhoff current law. IE is equal to IB plus IC. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.